Hi, my name is Andrew McLaren. Today I'm going to help you solve problems where you are trying to solve for the work given some force and displacement vectors. They may also have you looking for an angle, but I'm going to start with like the big picture here, which is the vectors, and then we'll relate to solving for the angle between two different vectors as well. How I'm going to do that is we're going to look at a simulation and then talk about the big picture and how these different things are related. And then we'll actually do a couple different example problems. One like the example that I have there, another one where they're actually also asking for the angle between these two vectors, and then also one where there's three dimensions and we're trying to find the angle between the two vectors there as well. So you should be able to solve any problem that has these three concepts by the end of this video, and you should be able to understand how the formula relates to those different examples. Okay, let's dive into it. So the big idea on this is that force and displacement is related to work through a relationship like this, where we've got the force times that displacement, but this is a dot product, which is also, you can write that out as force times displacement times cosine theta. This means that the force and displacement are really maximal when they're in the same direction. So if we look at some force and displacement as vectors, you can have this maybe be a force at some sort of angle and displacement at a different angle. And really what's important here is how much this angle is coming into play, because that's going to end up causing this force to help speed up the object a little bit more along that movement, that displacement. But it really depends on how much of it is in line with the x-axis movement. So if these two have a small angle, then the force, its like vector component, what I would call is, maybe this is force and this is force along the x-axis as a vector, that is going to be a bigger thing if this angle is smaller. So there's a pretty nice simulation that I found for this, where you can take two different vectors and see what their cross product looks like. So this isn't exactly for force and displacement, but you can imagine that if a force is perpendicular to the displacement, it isn't really contributing anything. But if it's getting to be a smaller angle, it contributes more. So that's why we're using cosine here as opposed to sine. Sine is more for cross products. Dot products work like this though. You really get a bigger, what they're showing in this like kind of yellowy, maybe green color there, is that is going to be a bigger uh, magnitude if these things line up more, as well as being bigger if these are individually pretty big, like the force or the displacement are larger, then you're going to do more work. So it should make sense generally in the simulation. And then what we end up doing for work, how I was trying to think of this is that you can use the work done in the x-axis and the work done in the y-axis to then figure out what the total work is. So it's like speeding it up a certain amount in the x-axis, which is really this x times the displacement. And then in the y-axis here, it's not really doing any work with it how it currently is written. So if you've got one of these vectors just going straight along the x-axis, you've just basically consider the work done along the x-axis. But a lot of times these two things are going to be at some sort of angle. So if we go back to that simulation, they might be at some sort of angle like this. So if they're at the same angle, their dot product is pretty easy. It's just the force times the displacement, because the cosine theta, when you've got cosine of 0 degrees, that's 1. So it's as big of a magnitude as it could be. So if we look at our situation here, I've drawn out a force that's going at the same angle as some displacement. So it's like a smaller force and a fairly large displacement. So what we can do is we can look at the work done in the x-axis and the work done in the y-axis, and you can actually just add those two things up. It's kind of weird because normally when you think about this, you can see that there's Pythagorean's theorem relating a, b, and c. So the a squared plus b squared is equal to c squared. But interestingly enough, you can just sum up the works. So I was trying to think about how or why this works that way. And it has a little bit to do with the force times the distance along those two different axes. And that force times that distance should be related to that kinetic energy. And so you can think about how fast it's going in the x-axis and how fast it's going in the y-axis and the total speed as well in general. And when you look at those, you can actually kind of sum them up by having the x squared and the y squared for the velocities. So we are still kind of seeing the um, a plus b, or a squared plus b squared is equal to c squared when we're talking about the work. It just kind of looks a little bit weird because you aren't really seeing the v's that are being squared. But that is the big picture for me, is that you just end up looking at the work in the x-axis, the work in the y-axis, and that will tell you how much this gets sped up by, which is a little bit easier to imagine when it's only the x-axis is only contributing to the total work, which it would be the case if one of the vectors was just going along the x-axis. But because both of these have components in the x and the y-axis, we need to contribute how much work is done along those two axes to get the total work. So if it's at a slightly different angle, then this is something that you can actually solve for. So if this is at a different angle, you can actually get the total work done and then compare that to how much could be done if x times the displacement and the total force were just multiplied. So you can do some math to solve for the total work that's being done here, and then compare that to how much potentially could be done if these two were just multiplied directly. And that can actually give you a relationship where you can solve for this angle theta. So if you are able to relate like this fraction is like, oh, maybe only half as much work is being done compared to what you might expect, then you can solve for that theta. In this case, if theta is 0, then these two things should be equal, the top and the bottom. The work total should be equal to the force times the displacement total if they just are in line, because you just multiply those two together, and it's kind of nice and easy in that case. So the work total is related to these two different work pieces. So you just basically look at combining these two different vectors, and then that should help you get this total amount of work done. And it's the same sort of idea for 3 dimensions. You just need to do the work in 3 different dimensions and solve for that. And it's the same sort of idea, really. Okay, all right, let's do it. So if we look at this problem, there's a couple things that I can see going on. We've got the force, but we do not have the displacement given, but we can see that the displacement is going to be like a change with the final minus initial. So we can do that for the x-axis, and we can do the same thing for the y-axis as well. And so we just need to look at these positions in the x-axis and in the y-axis. So if we're looking at this for the change in the x, I'm seeing that its final is 7.08 meters, and its initial was 3.39 meters. So we can get that displacement that in the x-axis pretty easily by doing that combination there. So we got that 7.08 minus 3.39. So that means our displacement is a positive 3.69 meters. So it's gone along the x-axis in the positive direction, 3.6 meters. And then if we do the y, because I is equal to x and then j is equal to y, those are the vectors, the letters that they write for them. So we can then plug those numbers in, and we have a final of 9.04 meters minus 5.09 meters. Just make sure you're being careful with the final initials and that you don't flip them. So it looks like this was, the final, and this was the initial. It looks like we have the correct numbers in the correct spots. Always a good idea to double check that though. And then we've got 9.04 minus 5.09. And I'm seeing 3.95 meters as that vector, a positive. So it looks like both the force and displacement are going up and to the right. It looks like this force is going up and to the right a certain amount. It looks like it's a little bit more in the y-axis than the x-axis right here. And then we've got this displacement, which is pretty even between the two. So it's kind of more like there. And so we can figure out how much work is being done, how much it's getting sped up by combining their x and y axes vector components. So if we look here, we can think like, okay, I've got this total work, and then I've got the work in the y-axis and the work in the x-axis. And this work in the x-axis is going to be the force in the x-axis times this displacement in that x-axis. So it's pretty easy to kind of plug in these numbers for this. But then we can add those two works up to get the work total. I talked about a little bit why in the previous section. So if you're unsure, maybe rewatch that section about why we can add those numbers up that way. So we've got the force in the x-axis. That's going to be 4.71 newtons times a displacement in the x-axis of plus 3.69 meters. And we can solve for that as a number now. And we've got 17.37 joules. Just got to add a couple extra sig figs on because this should be in the end 3 sig figs. But we just want to get that as the final step. Do the rounding as your final step for reported numbers. So we've got the x-axis, and now we need to do the same thing for the y. And I do like to give myself these labels just to make sure I'm getting the right numbers in the right spot. So I've got that 7.52 for the newtons, and then we are timesing that by a positive displacement of the y, that was 3.95. And when you have a newton times a meter, that's going to result in joules. If you kind of know what a joule is, then that helps you with these problems, just kind of knowing what units you're working with. So like a newton times a meter is equal to a joule. That's kind of useful for just working through these types of problems. So if we do that, 7.52 times 3.95, we get 29.704 joules. And so we've got the work in the x-axis and the work in the y-axis. If we want to get the work total, then you just add up those two different values. And it's pretty easy at this point. So we just add up our two numbers there. We've got 17.37 plus 29.704. And this is going to be 47.074 joules. This does get limited down to the 3 sig figs, I believe, at this point, because these problems were limited to 3 sig figs in terms of their accuracy. And you can then see the 3 sig figs being added here, when now it's more about place value. So it's really the 10th place value that's coming into play here. So yeah, this gets rounded to the 47.1 joules is what I'm seeing. And that should be good for this first problem. This wasn't asking for the angle, but we could just multiply the magnitude of the force times the magnitude of the displacement, which interestingly enough, they didn't give those values to us, so we'd have to solve for those. But then you could imagine that those two are going to multiply to a bigger number than 47. And then you can compare the magnitudes of those two numbers to get the angle. But this problem wasn't asking for that, so we're not going to do that for this one, but we'll do that in the next one. So this problem's a little bit easier in some regards because they give us the vectors, so we don't have to do final minus initial to get the displacement. We just have displacement as vectors. And then we can see the forces. One of them is actually negative, so we have a positive x-axis component for the force, but then a negative y component coming in there. So we've got this force total that's going downward a little bit. And then I'm seeing that there's this displacement that's now going positive in the x quite a bit and then positive in the y a little bit less than that. So it's kind of like at more of an angle like this. So this is the displacement total. And so we have some sort of situation here where the force is adding to it in one regard. In the x-axis, these things are kind of working together. But I think in the y-axis, they're actually kind of, it's getting slowed down a little bit due to that contribution in the y-axis. So I'm seeing this wx, that should be causing this to speed up because they're both positive in the x-axis. But the wy here is going to be negative. So this force is actually slowing this object down a little bit. So we need to contribute that as a negative number when we're figuring out what the total work is that's being done here. So this is similar, but it looks a little bit different. And we should be able to actually also solve for this angle between the two at the end. So we'll figure that out at the end. But for now, let's just figure out what the work is in the x-axis and how that work is in the y. So the work in the x-axis here, it looks like we have the force in the x-axis times that displacement in the x-axis, and we have that as a positive 1 Newton times a displacement of 5 meters. So the work in the x-axis is coming out as plus 5 joules, so it's getting sped up in that direction. And then the y is similar sort of formula, but it's different values because now we're in the y-axis. And now if we're talking about the force in the y-axis, this is a negative 4 newtons and a positive 2 meters. Now, if these both were negatives, like if this displacement was going downward a little bit on the y-axis, then it would be speeding up. But because these are kind of going in opposite directions, it slows it down. So I end up getting, what is that? Negative 8 joules there. So if we want to figure out what the total work is that's being done, you can add up the work in the x and the work in the y. So we've got a plus 5 joules in the x, and then a negative 8 joules in the y. Yeah, joules, it looks a little weird. We end up getting plus 3 joules of work being done. So we can see that there's a positive 3 joules of work being done. If we want to find the angle between these two things, what we're going to need is, first of all, we're going to need the magnitude of the force and the displacement. So the force total, we have the fx and the fy, so we should be able to solve for the ft. And it's the same sort of deal for the displacement here. We have that displacement in the y-axis, and we have that displacement in the x-axis. So we should be able to solve for that through squaring those different components. So we've got the x, which the force in the x was plus 1 Newton, and the force in the y was negative 4 newtons. So if we do the a squared plus b squared equals c squared here, we can do 1 Newton getting squared plus a negative 4 newtons getting squared is equal to the c squared. So we've got 1 squared, and then 4 squared is going to be 16. And we can solve for the c now. So I'm seeing, sorry, the 1 squared is 1 and the negative 4 squared is 16. So we get a 17 square newtons. If you were to think about the units on that, that's kind of what I would say for that. And then c by itself is just the square root of 17. 17 square root is 4.12. Okay, so we have some sort of f total there. And we can do the same sort of thing for our displacement. So instead of those forces in the x and y direction, we'll use the displacements. So the displacement in the x-axis was 5 meters, positive 5 meters, and in the y-axis that was a positive 2 meters. And so it's just a matter of taking the 5 meters, squaring that, and the 2 meters and squaring that. And that should be equal to our c squared. And so our c squared now is equal to, what is that, 5 squared? Is that, it's 25 plus 4 meters squared for both of those. So we get 29 meters squared for our c squared. And then we can isolate for c. If we do 29 and we do our square root of that, we get 5.385. And that is now going to be our displacement total. So what you might think here is that if we have the change in x total times the f total, then that could be like what ft would be if it was along the same axis. So it isn't quite along the same axis here, so it isn't going to be that value, but this is going to be useful. So we can just plug in these two numbers, 4.12 newtons times the 5.385 meters. This should be meters, this should be newtons. Then we can get that as a number. So I'm getting 4.12 times 5.385. We get that is 22.186 joules. That it's like saying that we could potentially have gotten that. So if we break this back down to the formula, the work total should be equal to the force total times this displacement total times cosine theta. And we basically have said like this times that is 22.186 joules. But when we do it times the cosine theta, this work was what we got earlier. So we have the 3 joules there. And so if we now rearrange this, we can get cosine theta is equal to the 3 joules over the 22.186 joules. So we can turn that into a nice simple ratio. 3 divided by 22.186. We can get that as a number, 0.135. 22 is equal to cosine theta, and then we can do our inverse of the cosine function on that and get that as an angle. So it looks like theta is equal to 82 degrees, 82.22. Just looking at the big picture, these things were not super accurate. They're only accurate to 1 sig fig originally, so we're probably limited to 1 sig fig here as well. So I'd say that this is about 80 degrees for the angle between the two. And if I'm looking at them, how we drew it, yeah, they do look like it's about 80 degrees between the two. There's very little of this actually being contributed along that direction. And if we go back to the simulation, you can see that one of our displacements kind of like that, and our other one's kind of like this. And that looks pretty similar to what we're seeing in terms of the general relationship in this problem. So yeah, that's the main idea when you're doing this in 2 dimensions and also trying to find that angle between them. Yeah. So if we have some forces in 3 directions and displacement in 3 dimensions as well, then we can find the overall work that's being done as well as the angle between the two. And it's the same sort of idea. We just need to add another dimension in. So when we're looking at this work now that's being done, there is actually 3 dimensions. So it's kind of hard to show this visually, but there is going to be a work in the y-axis, work in the x-axis, and then there's going to be some sort of work kind of in the z-axis. And so this overall work total now needs to contribute the 3 different works coming into play here. So we just need to solve for these values, 3 different values, and then add them up to get this work total. So the work total is now just equal to this work in the x-axis, work in the y-axis, and work in the z-axis being added up. So for this problem, we have work in the x-axis, that force in the x-axis times the displacement in the x-axis. So we have a force now that is plus 2 newtons. I'm seeing that 2i now there. times the displacement of a -1. So it's going down 1 meter. And so that is now kind of slowing things down in that x-axis. So we're getting a -2 joules of work being done along the x-axis. So it actually kind of gets slowed down because these things are fighting each other in a sense. They're going opposite directions. So a force that's not going with displacement should slow an object down if it's going against that displacement. So if we have then the work in the y direction, same sort of idea. And now we need to do the force in the y-axis, which I'm seeing a +1 Newton there. And I'm seeing a +2 meters there. So this is adding 2 joules of energy in the y-axis. And then we've got our work in the z-axis. And you can imagine how this is going to work, right? It's going to be +2 newtons for that k component there. And then +1 meters for the x-axis component. And so these end up adding together. So we end up getting +2 joules in the z. So if we end up plugging in the numbers here, we've got -2 joules, +2 joules, and +2 joules. So the work total overall is going to be, in this case, 2 joules. So that's pretty easy to do the first step here. But then the angle between these two is just like, it's a little bit more tricky. But if we want to find the work, we're going to need to get this force total, which is now equal to force in the x-axis squared plus the force in the y-axis squared plus force in the z-axis squared. This is kind of weird, but if you have multiple things coming together like this, you can get the magnitude in a similar way, but you've just got to add in this being squared. I could real quick get a diagram to show that. So this is an example of how the math works when you're trying to find the vector right here and its magnitude. There is a smaller triangle here where you have this being a leg, the c squared. And that is actually like if you combine x squared and y squared, you get this thing right there. So that's kind of like your x and y squared is kind of replacing c. And then you can have the z squared as well kind of coming into play as that third vector. And that will end up giving you, when you square all three of those, you end up getting the magnitude of that vector in 3 dimensions. So it's just kind of a little substitution going in there. And that's the main idea with how you can end up combining these in a similar way to Pythagorean theorem, but it's with 3 dimensions. So we can do the same sort of idea here that we did before with 2 dimensions. We just need to take the 2 newtons that we've got there, square that, plus the 1 newton there, square that, plus the 2 newtons here, and square that. And you can see that this is going to be a little bit weird, but we've got 4n squared plus 1n squared plus 4n squared. We add those up, we get, what is that? 9n squared. And so this ft squared is equal to that, and we can then just square root it, and you should be able to see at this point that that's going to be 3 newtons for the total force. And we can do the same sort of idea now, but for the displacement total, that should be squared, and that should be equal to these different components being squared as well. So we've got our displacement in the x-axis, which was a -1 meters. That's going to get squared. And we've got the other two also being squared. I'm seeing +2 meters and +1 meters. So we end up getting 1 squared plus 4m squared plus another 1m squared. We add those together, and I'm seeing that as a 6m squared is equal to this total displacement squared. And so this is just the square root of 6. We get like 2.449. And we can then combine those two to get like what would be this work total if we just combine the two there. So we can then combine the 3 newtons with the 2.449 meters and get that as a number of joules. And we get 7.347 joules of work that could be done if these things were lined up perfectly with each other, but that isn't actually the case. So this work total is going to be the F total times the displacement total times the cosine of the angle between the two. We've said that these two times each other would be the 7.347 joules, the work total we had found previously in the last section. So I believe that that work total was 2 joules. And so we're able to say that this is the 2 joules, and we can rearrange to isolate for the cosine. So we've got 2 divided by 7.347, and we're getting that as a fraction. And I would encourage you to write that out before you do the trig function. It's just nice to be able to double check that. So then we're going to do a cosine on that, and I'm getting an angle of 74 degrees. Which kind of makes sense because there's not much work being done, though there could be if these two were lined up, and so we're getting a pretty small fraction, so this cosine is at a significantly different angle. The force is at a pretty different angle than the displacement. It's hard to do this in 3 dimensions, but we can kind of see that this is 70 something degrees, so it's kind of like that, where we've got these two numbers being multiplied together, but they're significantly not going in the same direction, so you don't get much work being done because their vectors don't line up that well. So yeah, that's the how you do a problem like this in 3 dimensions. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.